And good evening, everyone. If I could just ask our programme coordinator to introduce this evening's speaker.
Good evening. Tonight we welcome a regular visitor to our society, Dr. Brad Gibson. Brad is the scientific editor for the Astrophysical Journal and has previously served as head of physics and maths and director and founder of the E.A. Milne Centre for Astrophysics at the University of Hull. He's also been chair in theoretical astrophysics at the University of Central Lancashire and deputy head of school at Swinburne University in Australia. Brad's research teams in the past have been responsible for first defining the Milky Way's galactic habitable zone and determining the expansion rate of the universe, for which their team was awarded the Gruber Prize in Cosmology. And he's also been responsible for building the world's first liquid mirror telescope observatory. Brad's 1,000 plus outreach events over the past 7 years have reached 2 million people around the world. So let's give a big Mexican Swinton welcome to Brad Gibson.
Thank you yet again for having me back. I always love coming to see you. One of my first societies that I came, when I got on this 1,000 run of outreach talks, it was one of the first ones that I came to, so it still has a soft spot in my heart. Even if the venue does change every time, but I appreciate the opportunity to come back. So tonight, what I'm going to talk about, it kind of pulls together a few different strands of some other talks that I possibly have given here and have given elsewhere in terms of the origin of the chemical elements, the impact of the galactic habitable zone and where you might find life. They all depend upon, both in a good way and a bad way, with this topic tonight of stellar winds, and hence the subtitle of Givers and Takers of Life, because they're a very complex little beast. And normally when we talk about stellar winds, the immediate thing that usually comes to mind is the most extreme of the stellar winds, and that is a supernova. Stars that are 10, 20, 50, 100 times heavier than the sun. They live fast, they die young, they explode spectacularly. They provide us with fabulous things to look at through our telescopes, various supernova remnants, Crab Nebula. They also provide everything that you can see with your eyeballs right now, including your eyeballs, all those chemical elements that were made out of the carbon, the iron, silver, gold, everything else that you can think of generally comes from one of these exploding stars. And so there's an entire cottage industry around trying to understand the science of these exploding stars and the origin of the chemical elements, how those exploding stars interact with their environment. And as I say, they do provide lots of fabulous things to look at through a telescope. And so normally that's the thing that people think of when they think of things blowing off of stars, is those spectacular supernova remnants that are left behind at the end. I will touch on them along the way, but I'm going to focus more on some other angles around stellar winds. And there's an entire zoo of stellar winds and an entire taxonomy around the different types of stellar winds. So I'll start with the most sedate, in some sense, the solar wind, and stars like the sun that are sort of midway through their life, happily burning hydrogen into helium. They generate winds. Nothing as spectacular as the supernova that I just showed you, but they do generate winds, and those winds are really important. And now the winds that come from the sun are largely driven not by the action that's going on down in the center of the star, where nuclear fusion is occurring and hydrogen's being burned into helium. It's actually driven largely by, if you like, the atmosphere, the corona of the sun. The corona of the sun is much, much hotter than the core of the sun. The corona, the outer atmosphere of the sun, is millions of degrees rather than 6,000 degrees or so, or whatever it is down in the center of the sun. So it's much, much hotter. It's also very magnetized. And what that hot magnetized corona or halo of the sun does it provides an enormous amount of energy to push away charged particles, particles that feel that magnetic field, whether they're a positive charge or a negative charge, a proton or an electron, for example. And those get accelerated to pretty high speeds, hundreds of kilometers per second. We'll come to bigger numbers in a few slides. But it generates that hot magnetized halo, provides enough energy to push those charged particles, which are the wind, at a speed which is greater than the escape velocity of the sun. So they're not held on by the gravity of the sun. They go screaming outwards across the solar system, and they happen to play a very important role, as I'll come to in just a second. Now, that's a star like the sun, which is sort of midway through its life cycle. Happily, doesn't change much on a day-to-day cycle. Toward, in 5 billion years, when that energy, that hydrogen that gets converted to helium starts to get depleted, and the star comes towards the end of its life, it ends up going through a red giant phase, and you're able to puff off the outer atmosphere, not just blowing off little wisps of high energy cosmic rays that are sort of blasting out. You're able to start blasting off huge amounts of mass. And so a star, a system like this one, NGC 6565, the classical planetary nebula, where there's a hot little white dwarf remnant left down in the very center of that planetary nebula. And the radiation from that white dwarf is able to push off the outer atmosphere, which is what you're seeing, those beautiful things like the Ring Nebula and things like 6565 there. The radiation, not the hot magnetized corona, which is what was pushing the solar wind, but the radiation itself is able to push the cold, cooler outer atmosphere of, say, the red giant and push it away at not hundreds of kilometers per second, but moderate speeds, a few kilometers per second. But you can start to push off, that radiation is able to push off slowly, but it pushes off a significant fraction of the mass of that star. Something like the sun may lose roughly, say, half of its mass will get lost during this phase of blowing off the outer atmosphere. And that outer atmosphere, the different colors there are different chemical elements that ultimately get pushed out into the interstellar medium and get incorporated into the next generation of stars. So things like carbon and nitrogen and lead largely come from stars like our sun at the end of their lifetime, as that radiation pushes off the outer atmosphere of these red giants. If you move up the scale in terms of mass, things that are 10 times, 20 times, 50 times, 100 times heavier than the sun, they don't end their life with a nice quiet puffing off of the outer atmosphere, that planetary nebula. They end their lives typically in those spectacular supernovae that I showed you a couple of slides ago. And this is just one example of one that is towards the end of its life, LL Orionis. That's about 40 times heavier than the sun. It's losing about a solar mass every million years or so, getting blasted off at significantly higher speeds, kind of thousands of kilometers per second, rather than the planetary nebula, which is coming out at a few kilometers per second. So you're blasting off a significant fraction of mass at pretty high speeds from these stars that are on the verge of becoming sort of supernova. And again, this is before the star actually explodes, but it's getting towards the end of its lifetime. And that radiation pushes on, again, those atoms that we know and love, like carbon, like nitrogen. Lots of the other chemical elements are getting pushed off by this intense radiation at high speeds, again, much greater than the escape velocity of the star, so they're able to completely escape that system. And those chemical elements get pushed out into the interstellar medium and again get incorporated into the next generation of stars, and the cycle continues. And this is just another example of one of these massive stars, roughly, again, about 40 times heavier than the sun, NGC 7635. And in this picture, though, you can see the explosion as it's imminent or just beginning. And you can see the bubble, a very clear picture of a bubble sitting there, which is being accelerated outwards again by the radiation of the star just before it explodes. And then when the star explodes, it'll do significantly more damage. But for scale, that bubble that you see on the slide right now, that's about 10,000 times larger than the bubble that our sun has pushed, which I'm going to come to in just a second. There's a special type of name called a heliosphere. So that is a much larger bubble, and it's kind of sweeping up material as it's being pushed up, leaving not a perfect vacuum behind, but it's, you know, a pretty empty space inside of that bubble as the bubble continues to push the surrounding material away from it. So these are the sort of the 4 points, kind of the touches on each of the zoo that I've just discussed, the taxonomy that surrounds stellar winds. And so these are the 4 points. I'll spend sort of, you know, 5 to 10 minutes on each of them. I've given you the introduction to the solar wind. I'll talk about the heliopause and what that is, the heliosphere, heliopause, you'll hear different terms mentioned. So that's on a very local scale around the solar system. We go a little bit further to the sort of surrounding solar neighborhood. We sit inside a thing called the local bubble. And more or less what it sounds like. It's a bubble that's been sort of been created by stars in the past exploding and pushing things out of the way. So we live in a pretty empty region of our Milky Way inside of this thing called the local bubble. It plays a really critical role in shaping what galaxies look like. You know, the spiral galaxies have lots of structure and look really beautiful when you take all these pictures. And that's because you've got these massive star winds that are sculpting and shaping the galaxy to give it the beautiful grand design spiral structure that you actually observe. Then you can look at go even further and look at the role that stellar winds play in generating galaxies. Why do some galaxies look like Andromeda or Milky Way? Why do some galaxies look really smooth, giant elliptical galaxies? There are fundamental differences, and a big part of that difference is driven by the stellar winds that shape and sculpt the interstellar medium and ultimately play a huge role in determining what type of galaxy you are actually going to end up with. And then I'll end a little on something I've alluded to there, the role that winds play in shaping the chemistry of our universe and the chemistry that results in our life and our terrestrial planets. Again, there's tons and tons of talks out there that talk about the role that supernova and exploding stars play in shaping the chemistry of the universe, and they are fundamentally important to the generation of a lot of the heavy chemical elements that we know and love. But the winds, the pre-supernova winds that do all of these things of shaping and sculpting, they're also really, really important for generating a significant number of the chemical elements that are responsible for the development of life. So I will mention supernova and talk about them a little bit along the way, but I want to focus more on the role that the winds play in shaping galaxies, in seeding galaxies with the basic ingredients for the development of life, and just sort of bypass the really explosive supernova. So solar wind, I apologize, you won't be able to read the small little writing, but if you've got really good eyes down in the center, you will see the solar system, the little yellow dot in the middle, there's the sun, and there's a few little circles, which are the planets that we know and love. And our solar system sits within this thing called the heliosphere. Now, it's not a perfect sphere. It's kind of this elongated, blobby, sort of football-shaped thing, or American football-shaped thing, that changes its shape because our solar system is moving through a galaxy, and we go from regions where there's a bit more stuff around to regions where there's less stuff around. The shape of this heliosphere changes a little bit with time, but you've got this heliosphere, which is a bubble that's been driven by that solar wind that I talked about. The magnetic field around the sun pushes cosmic rays outwards and creates this bubble around us called the heliosphere. And where that heliosphere ends, if you like, if you've got good eyes, you'll see something called the heliopause. And that's basically where the bubble stops expanding, because that's where you balance the pressure of the surrounding interstellar medium with the pressure that the solar wind can actually generate. And that's kind of where it ends. And then you'll hear terminology, something called the termination shock, which is where the expanding bubble goes from greater than the speed of sound and drops below the speed of sound. It's still moving outwards, but it's dropped below the speed of sound. Gory details don't really matter. But the key thing is we sit within this bubble, and the really important thing from our perspective, is that not only does our sun generate cosmic rays, and I will come back to the cosmic rays that are generated by our sun and what they do to our Earth and other planets within the solar system, but all stars generate cosmic rays, super high energy cosmic rays, exploding stars before they explode. You can get these cosmic rays that blast us from all different directions throughout the galaxy as we travel around. Cosmic rays, they're nasty. They are thought to be one of the limiters for the development of life on other planets. Once, the first DNA forms and RNA, these cosmic rays are able to blast apart DNA before it can ever sort of take root and become something more complex. So if you want, like the romantic idea of life being not common, at least not uncommon, what you don't want is to have your planet being bathed with cosmic rays, super high energy particles blasting the surface of your planet all the time. Really difficult for complex molecules, complex biological structures to survive when they're getting blasted by cosmic rays. The beautiful thing about this heliosphere and the heliopause is it effectively acts like a shield. It protects us from this bath of high energy cosmic rays that are coming at us from different directions. It doesn't block all of them, but about 90% of the really high energy cosmic rays that are coming at us from all of our surrounding neighbors are blocked by that heliopause. So it's a good thing that we have a stellar wind, and it's responsible for other nice things like the aurora borealis and australis. We'll come back to in a second. But it plays a fundamental role in, doesn't necessarily mean life will take root, but it provides a shield that protects us from 90% of the highest energy cosmic rays that otherwise would make it to the surface, make it to the inner part of the solar system. So it doesn't get a fair discussion in we're talking about the ingredients of life, but it is an important one. We take a step further out from the immediate solar system and the impact of the solar wind in generating this heliosphere around us. Our solar system, our sun, sits within this thing called the local bubble. Now, we don't have too many big stars that are super close to us right now, but if you look back over 10, 20 million years or so, there have been some stars that have exploded not too far from us. And we have some stars that are potentially going to turn supernova soon. We've all heard, every once in a while you get a story about Betelgeuse about to explode a couple of years ago. Antares, that's also one probably in the next 10,000 years, so you don't have to lose sleep over it. That's also going to probably explode on that sort of time scale. But each of these big stars that you see there, Antares, Beta Canis Majoris, Betelgeuse, they're not super close to us. They're about 500 light years away from us, each of them. But they have each, because they're massive, they've sculpted and blown out bubbles around their own star. Our sun is just a piddly little bubble compared to the bubbles that these bigger stars have created. And the generation of stars which exploded 5, 10, 15, 20 million years ago in the vicinity have also helped push out this bubble around us. So again, it's not a perfect spherical bubble, which you might think of when you hear the term bubble, but there is this local bubble shaped thing where, again, the interstellar medium, the gas and the dust that defines the disk of the Milky Way has been really pushed out to significant different distances around each of those stars, and they've overlapped and have given us this underdense region that we live in right now that we call the local bubble. And so those winds, even before, Antares, Beta Canis Majoris, Beetles, those stars haven't exploded yet, but they have really helped push out this bubble and have these bubbles overlap with each other to give you this larger local bubble. And it's, like I said, taken a smooth interstellar medium, smooth distribution of gas and dust, created these bubbles. It loosens things up, makes things more turbulent as it is. Instead of being nice and smooth and calm, it churns things up, makes things turbulent, so that when one of these stars do explode, whether it's Antares or Betelgeuse going off in 1,000 years or 10,000 years, they explode inside of a region where things have become jumbled and pushed away and loosened up a little bit. So when they do explode, they're much more efficient at pushing things even further away. Instead of exploding in something which is kind of smooth and dense, so a lot of the explosion energy doesn't go very far. It does push things out, but maybe not as far. But by exploding inside of the local bubble where everything has been churned up and loosened up a little bit, it's much more efficient at pushing things much further away. So that's important for pushing chemical elements further away, but it's also important for shaping the galaxy, as I'll come back to in a second. Oh yeah, we'll do it from, rather than looking at a local bubble scale, I'm now going to just jump from small little part of our galaxy to the entire universe. A very common slide that's used, I think if you Google image cosmology or something, is probably the #1 ranked image, which is used and abused in almost every talk. And it captures the universe in a very simple cartoon, going from the left, where you've got the Big Bang, to today with some satellite looking back in time to the left. And I'm not going to spend any time talking about what happened before the Big Bang or what's going to happen in the distant future. But we started off with a really small, super dense universe, which very, very hot, very, very dense, with little quantum fluctuations inside of it. Something kickstarts the Big Bang, whatever that might be, and the universe goes through a very rapid inflation, as it's called, for a few 100,000 years or so. And the universe goes from being very, very hot, so hot that in those first few minutes, there's not a whole lot in the way of chemical elements except hydrogen and helium. And if you cast your mind back, what is hydrogen is a positive proton and a negative electron, and they stick together. Helium is 2 positive protons, a couple of neutrons, and a couple of negative electrons, and they stick together. But in those first few 100,000 years, the universe is so hot and so dense that all of those electrons that are normally stuck onto their protons, they all get stripped off. And you end up having this background fog of electrons everywhere. Why is that important? Well, those electrons, because the universe is expanding, but it's still really, really small and filled with this fog of electrons. And it's so dense with this fog of electrons that the energy, the light, if you like, from the cosmic light, from the Big Bang, can't actually really move anywhere. The photons, they're not maybe photons that your eyeballs or your telescopes here would observe, but there's still energy, it's still photons, but they can't really move anywhere. So the universe, when we look back in time, we can't see the Big Bang. We can't see 2 years after the Big Bang, 10 years after the Big Bang, 1,000 years after the Big Bang, because you just hit this wall, this fog, this sea of electrons where no energy can get through. The energy just bounces around in the universe. Because the universe continues to expand, as it gets bigger and bigger and bigger, it's cooling and cooling and cooling in temperature. And then after about 300,000 or 400,000 years, the universe becomes cool enough that that fog of electrons, instead of just floating around all over the place, blocking the light, they're able to connect back up to their protons. And so the fog is lifted, and then that energy, those photons from the Big Bang, stream across the universe. And we see that today as this thing called the cosmic microwave background. And if you have a telescope, which is not sensitive to the optical photons that our eyeballs and ground-based telescopes largely are, if you've got a telescope that's sensitive to microwaves, and you took a picture of the sky, it would look something like this mottled colored pattern that you see on the screen. where the blue areas are teensy tiny bit cooler in temperature and the red areas are teensy tiny bit warmer. Only like a part in 100,000. It's not like one of them is 1,000 degrees and one's, minus 1,000 degrees, whatever. They're all basically the same temperature, just subtle differences. And those subtle temperature differences, effectively the entire history of the universe is encoded in there. It tells you how much matter there is in the universe, how much of the matter is normal stuff that we're made out of, how much of it is dark matter, how much of it is even more mysterious dark energy and how important that is, how old the universe is, likely what the future of the universe is going to look like. There's everything is encoded inside of those subtle little patterns that may look random to the eye, but you can tease out an enormous amount of physics. And when you look at that, that cosmic microwave background, whether you look at how galaxies rotate, how they spin around, like the Milky Way spins around like a giant flywheel. If you look at that cartoon starting on the right today and just count galaxies as you go backwards in time and see the number increase and then decrease, all of that is different ways of answering the same question. It tells you that of the matter in the universe, I'm not going to talk about mysterious dark energy, but of the stuff, the matter in the universe, 1 part in 7, 15% of it is the normal stuff that we're made out of. The normal things you see in the periodic table, carbon, oxygen, and iron, and uranium, et cetera, et cetera. 85% of it is mysterious dark matter. We know it's there. We can feel it through its effect of gravity, but we can't see it. We can't point a telescope and see dark matter. It doesn't emit light. It doesn't absorb light. It just influences gravity. And so the dark matter is, the other 6/7 of the matter content of the universe. It dominates the matter content of the universe, and it only interacts via gravity. Why do we care about that? Well, what it means is that inside of a computer, it's really easy to run a computer simulation of the universe and get something that looks like the universe today, because the only physics in it is gravity, and that's the inverse square law. So the inverse square law, if you're sitting in the front row, you hear certain decibels of my voice. If you're 2 times further away, you're hearing my voice not 2 times quieter, but 2 times 2, 4 times quieter. If you were 10 times further away, my voice would sound 10 times 10, 100 times quieter. And that's because it goes as the square of the distance, just like electricity, magnetism, light, gravity. But what that means is it's really simple inside of a computer. You can have millions and millions of little particles. There are billions of particles that represent galaxies. And while it may take a while to run the computer simulation, there's no tricky physics in it. That's all there is to it, is the inverse square law. If a particle is really close, it feels the gravity of the neighboring particle really high. If the particle is further away, then the gravity influence is much lower. If it's 10 times further away, it's 100 times lower. There's no other complicated physics in these computer simulations. And it means you can generate a simulation like this on the right and compare it with observational data on the left. And you can count how many galaxies are in this computer simulation, how many of the galaxies are in filaments with stuff connecting them, how much of that computer simulation is empty, what we call a void. And so when you take these computer simulations with nothing but this, you start with the cosmic microwave background and you just turn on gravity and you don't do anything else, you can generate something that looks more or less exactly like our universe today with really simple physics, which is great. The problem is when you take the next step and you try to do the same thing and generate something, say, inside of a computer that looks like our galaxy or Andromeda galaxy, a beautiful spiral galaxy. The first attempts to do that, but 45, 46 years ago, this was one of the first galaxy simulation using nothing but that simple inverse square law of gravity, really simple gravity. And what Simon White did is he took a couple of galaxies, you can see up here in the starting point, and he just threw them at each other in different ways. Sometimes they collided straight on, sometimes they orbited around each other and spiraled inwards. He tried lots and lots and lots of different combinations to try and get something that looked like the Milky Way or Andromeda, a spiral galaxy. And he couldn't get anything that looked like a spiral galaxy. They always ended up as just blobs, like an elliptical galaxy without any structure, no spiral arms. They weren't rotating around, spinning around on their axis. So even though simple physics gave you a beautiful simulation of the entire universe, simple physics couldn't give you something that looked like the classical grand design spirals that we know and love. And it comes back to what I was just saying a second ago. 85% of the matter in the universe is dark matter. So again, it's really easy. You only have to put in the inverse square law. You don't have to put any complex physics. You don't have to worry about what's generating light and what's not generating light. And that's the problem. You can't see dark matter. You point a telescope at the sky, you're going to see the normal matter, the stuff that is the 15%. The problem is that normal matter, sometimes called baryonic matter, that 15%, that's where all the complex physics is, really complex, and it gets into something called fluid dynamics and hydrodynamics. The reason being, say, a gas, like a gas, yes, if you have a blob of gas in space, it feels gravity, but it's like a liquid as well. It feels itself, it feels viscosity. And so it will heat up and it will cool down depending on what happens to it. And that changes its properties. And the physics that goes into how the gas heats up and cools down, how the light gets generated, how the energy gets generated, that's where all the gory complex physics comes into play. And so that's basically what captures computational astrophysics in a nutshell. Is everything I've talked about so far is, it's basic A-level, it's inverse square law. You can get something that looks, a reasonable universe that looks like the real universe. But if you want to get something that takes into account the physics of gas and the physics of stars, then you have to worry about this thing called viscosity. That's what fluids are. Both of these are things that are done at A-level physics. There's nothing more complicated that goes in, but in terms of running a computer simulation, the painful part of the process is that second point, fluid flow. And you can think of gas as just, a really dilute, super dilute fluid, if you like. And viscosity, you encounter it, all the time, right? You take a glass of water, you pour it out, it sloshes around in a way that you know what's going to happen. You do the same thing with treacle or golden syrup. It's still a liquid. You pour it in, but it sloshes quite differently because it's a lot more viscous than the water. They're all obeying the exact same laws of fluids, but modeling that is a lot more complicated than just worrying about the inverse square law of gravity. So that's basically what people realized they needed to do something a little more complicated than just the inverse square law. And so this is what we do with my group as well, is we take a large pile of particles, if you like, and 85% of them only feel gravity. That's what the dark matter is. We don't care about, they don't generate light, they don't absorb light, they don't have any complex physics. That's easy. 15% of the particles, yes, they still feel gravity, but they also feel viscosity. Depending on how dense the environment is, the fluid or the gas is different. It heats up differently, it cools down differently. But it's the exact same technique that is used in, automotive aerospace engineering, designing planes, trains, and automobiles, working out the flow of air over a car or caravan, or designing Formula One cars. They're doing exactly the same thing, largely using astrophysical software. In fact, obviously in a very different environment than what we're doing. But this is what we did. This is what the first attempts took the inverse square law for 85% of the particles, and then 15% they added viscosity. That would be the gas and stars. And that was the hope that they were going to get things that look like these sort of, the grand design spiral you see in the top left, ones that look like lovely pinwheels when you look down from the top and look really thin when you look at them from the side. They have relatively small bulges in the center. They're not just, big blobby amorphous looking things, which the first simulations look like. You want to see some nice spiral arms in there as well. So that was what the hope would be when we put in the viscosity. And the first attempts, and this is only sort of 30 years ago, the very first attempts to include fluid dynamics, got things that were kind of like disk galaxies. If you looked at them from the top, they kind of look round. If you turn them sideways, you can tell they're not just round blobs anymore. These things are sort of rotating around, spinning around like the Milky Way does, but they're not thin and extended with little bulges in the center and lovely spiral arms. Yes, they are spinning around, but they're quite stubby and quite thick. And so those first generation of simulations, nothing looked, even though they were rotating, so they were disk galaxies, they didn't look anything like the grand design spirals that we know and love. And you can go forward up to sort of 15 years ago or so, with all the improvements to software and hardware that came along, you still got things that look like disk galaxies, but they still have really massive bulges, lots and lots of stars piled up in the center. Even if there was a little disk rotating around, like you get with a spiral galaxy, way too much stuff was piling up in the center and giving you galaxies that didn't look like real galaxies, even though they were a little bit better than the first generations, which didn't include any of the viscosity of the fluids. And so we recognized right away that we had to stop the gas, which ultimately is what forms stars. And the gas piles up, it gets dense, it eventually turns into stars. But what was happening was the gas just kept piling up down in the center of these galaxies. So even though gas was falling in and some of it was spinning around to form a spiral galaxy, a disk, way too much of it was piling up in the center, and way too many stars were being formed in the center of the galaxy rather than out in the spiral arms and in the outskirts, which is where most stars end up forming. And so we needed a way to take advantage of the energy that's involved and use some of that energy to push back on the gas that piles up in the center. And we sort of alluded to that already. Stars explode, they create a lot of energy. And before they explode, they can push things around. And so if you take an individual supernova, one exploding star goes off in our galaxy roughly once a century, one goes off. You can read how much energy it generates there on the screen. The number is more or less meaningless, a billion, billion, billion times more powerful than the most powerful nuclear weapon on Earth. So you've got a huge amount of energy when you take into account, you've had, a billion of these things have gone off, 10 billion of these things, 100 billion of these things have gone off over the entire life cycle of the galaxy. So it's an enormous amount of energy to play with. And the thinking in all of those early generations was that's where all the energy comes from. We know stars explode and very quickly dump an enormous amount of energy out there. And so all of those first generations of the simulations in the 1990s and the aughties, that's what they did. They just took that amount of energy from a star that explodes, put that into their simulation, but it wasn't enough. It helped things a little bit, but you still didn't get anything that looked like a real galaxy. And so this is kind of where we came into, link back to where I started, was that these stars that are 20, 30, 50, 100 times heavier than the sun, they blow these winds, they create these bubbles, they create things like local bubbles around that exist around our own solar system. And they can generate as much energy or more than an exploding star. And that was, it seems obvious in retrospect, but that was just something that got ignored for a long time because nobody thought stellar winds would play an important role in shaping things on this sort of large scale. And I guess the only thing I would take for that, ignore the bottom one, but if you look at the plot in the top, it just says it's time going horizontally, and it's the amount of power being generated every second on the vertical axis. And the main point being, you've got good eyes. Over those first few million, 10 million years, there's a lot of energy that's being generated every second by the stellar wind before it ever explodes. As much energy as being generated by the explosion, which happens after, in this case, 10 million years or so. And so again, in retrospect, it seems like a very common thing. And why wasn't this thought of? I don't know, it just wasn't. And that's where we came into play about between 10 to 15 years ago in a series of paper. We first really tap into that energy that got generated by massive stars before they ever exploded, and included that into our simulations. And here's this is what we got when we put in the stellar wind contribution on top of the supernova contribution. A couple of observed spirals in the top there, the top two pictures, and then the bottom two pictures below are one generated by my PhD student about 13 years ago or so, I guess. And while you can always find fault and there's little things that need to be done better, these are the first simulations that actually look like real galaxies. And that was what the secret was. Just the inclusion of all of that stellar wind energy before the star ever exploded. It plays a fundamental role in the generation of spiral galaxies. We cannot get them unless we take into account stellar winds. We would not have a spiral galaxy if we didn't have the stellar winds blowing bubbles around before stars start to explode. And you can play this. Chris, my student, generated this plot. I've never bothered to pin down which of the 6 are real and which of the 6 are fake that he generated. If you're an aficionado, there may be some NGC or Messier object in there that you know and love, but I don't know which ones are fake and which ones are real. So that's sort of the state of the art today. And then the last thing I wanted to say was about more than just focus a lot on the sculpting, whether it's the heliopause around the sun protecting us from cosmic rays, whether it's the local bubble, which has made things loose and turbulent, and then incorporating all of that into computer simulations that allowed us to generate galaxies that look like real galaxies finally. They are more than that. And you know, I've talked about it already in passing along the way. This is a different way of looking at the periodic table. And again, there's lots of variants of this out there now in Google Images. You rarely see, if you're an astronomer giving a talk, you rarely see the standard periodic table with a white background and a black label, you know, the ones that I knew and loved growing up. Nowadays, they're always color-coded by the type of astronomical object that is responsible for the generation of the particular element in question. And so you'll get, you know, the blue ones at the top are largely coming from stuff that was generated during the Big Bang with that hydrogen and the helium. The green, most of the, these ones are a lot rarer, ones that come from, you know, merging neutron stars and black holes. The green ones, you know, it's probably 95% of the atoms, taking out hydrogen and helium, you know, 95% of the atoms in the universe are those green ones that are in there. So you've got things like carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium. A lot of those come from exploding massive stars. So most of these sort of plots that you see write down exploding massive stars. But that's, again, coming back to giving, you know, proper lip service to stellar winds. That's lumping in that these things should not be green. They should be split between how much of it is generated by the explosion, the supernova, and how much of it was generated and spit out before the star ever exploded from the pre-supernova wind phase. And again, for those who were interested in modeling the chemical evolution of galaxies, which is what my PhD was all about, you know, back in the day, I just, like everyone else, whatever happened before the star exploded, who cares? Nothing. That's just, you know, in the noise. They don't even, just like we ignored the energy, we ignored the chemical elements that came out before the star ever exploded. We now know better, and so this should be presented in a different way, and the green should be split up between supernova and during the wind phase. And just to, you know, 2 examples just to demonstrate, again, what's on the vertical doesn't really matter. It's just the amount of particular chemical elements that are being generated by stars. And along the horizontal is the mass of the star. So things that are around 10, 12, 15, 20 solar masses heavier than the sun, most of it comes, you know, the helium comes from the explosion. The oxygen comes from the explosion. Carbon largely comes from the explosion. Most of the chemical elements come from the explosion process, and that's sort of fine. But as you move to heavier stars, 25, 30, 40, 50, 60, 70, 80, actually, the stuff that is the horizontal lines going in there is winds. So the helium, the carbon, the oxygen, it all gets generated before the star ever explodes. And that was what was being swept under the rug in all of that. And if you like your obscure chemical elements, this is fluorine on what going up and down and oxygen going across. If all I was interested in was fluorine that comes from exploding stars, I would make a model of our galaxy and I would get this dark line that goes along the bottom. And that's only accounts for about 1/3 of the fluorine in the universe. All of the stars that we take pictures of and take spectra of and look at the fluorine line always had 3 times ignored the fact that most of the fluorine actually comes out before the star ever explodes. And when you take that into account, you get this dashed line that goes more or less through the data. So again, fluorine may not be the most critically important chemical element in the universe, although if you're worried about your teeth as I am, because I'm suffering through a horrific toothache right now, fluorine is an important thing. So come back to where I started, just to end on this one. And I've got a whole talk on this colonizing Mars, which we can save for another day. There's lots of reasons why I don't think we're going to colonize Mars. And I'm sure if Elon Musk was here, he'd be arguing against that. And there's lots of things. And you can look at the fact that, that you can't grow anything in the soil, the impact of the lack of gravity. There's no atmosphere. It's super cold. There's lots of things you have to worry about. If you talk to astronauts, they don't care about any of that. They say it's the psychology, because you're gonna, you go there and you're gonna spend the rest of your life just talking to the 6 other people who are there with you, because it takes 20 minutes. You're never gonna have a live conversation with anyone on Earth again, so you're never gonna talk to anyone except those 6 people around you. So they all say exactly the same thing, that is the thing that worries them the most, is the psychology. But yeah, I've got a whole TED talk on that if you're interested. But anyways, stellar winds, why is it important? I kind of alluded to this one already. Look, Earth has an atmosphere, and that's because we have a magnetic field. We've got this hot, churning, molten core inside the Earth, which generates a beautiful magnetic field, gives us the aurora we talked about. More importantly, it acts as a doubly important magnetic shield that protects us from these cosmic rays that are blasting us from the sun. Mars does not have an atmosphere, does not have a magnetic field because its core is cooled down. That's why it doesn't have an atmosphere. It only takes a few million years or so, for even at the distance of Mars is from the sun. Without an atmosphere, even if you could establish an atmosphere on Mars, it would get evaporated by the cosmic rays from the sun over the course of a few million years or so. So if you want surface life to develop, you really do need an atmosphere, because the radiation levels are extreme. Gamma rays and X-rays, if you don't have an atmosphere, deadly. And if you want proof of that, again, the numbers don't really matter so much, but if you were to take sort of call a CAT scan of your body, call that the number 1. Scott Kelly spent a year in space. That's the equivalent of about, having 150 CAT scans, full body CAT scans. A Mars mission, that doesn't take into account, staying there, but just sort of going to Mars and back. That's like getting over 1,000 CAT scans on your body. It's not very good. And it does, significant genetic damage. I encourage you, if you haven't read it, Scott Kelly, this astronaut, got a twin brother. And so they did this experiment, and he was also an astronaut, but Scott was in space for a year while his brother was on Earth, and they were able to do detailed, comparison of the genetic damage that the year in space spent compared with his twin brother who had stayed on Earth. It's somewhat scary. So not having a magnetic field means you don't have an atmosphere, which means even on the surface of Mars, you've got 1,000 times more damaging radiation at the surface of Mars. And so you're going to have to live underground, or at least with meter-thick steel walls to protect you from that damage. And, you can do that. It's not going to be fun, but, you can do it. But that's one of the really important roles that damaging effects that a solar wind can have. By not having a magnetic field, you don't have an atmosphere, which means no surface life is going to develop. Maybe subterranean or something possibly. So final scorecard on all this: are the givers of life, takers of life? Mostly givers of life. like I said, the heliopause looking locally provides protection from interstellar cosmic rays. It's the source of critical elements for the development of life. A lot of the carbon and oxygen, helium, and somewhat more obscure elements like fluorine do come from stellar winds before a star ever explodes. And for me, who was doing these computer simulations, it solved this decades-long problem that nobody could get a realistic spiral galaxy inside of a computer. And that's because they didn't include the important energy contribution from stellar winds before the star ever explodes. So those are all givers. And then the takers, well, they like to take away planetary atmospheres. So unless you've got a magnetic field, or you can generate a magnetic shield between you and the sun, which, you know, maybe for around in a gazillion years, Elon Musk or his disembodied head will create some sort of magnetic shield, you know, at some point between us and the sun that will provide that protection that would allow one to reestablish an atmosphere on the surface of Mars. So I think that's everything I want to say. Yes, thank you.
Thank you very much, Brad. So we are now at the the point of our questions and answers of the evening. So anyone online, please put a digital hand up if you have a question. And anyone in the room, wave a hand. I don't accept bribes, unlike some other members of this society. You can ask your question free of charge. Okay, but what we are going to do tonight is we're going to hand around a little lapel mic just so the online audience can actually hear. So we'll give this a bit of a trial.
Thank you very much, Brad. Very interesting talk. You spoke about the heliosphere, and it would be an American football shape rather than a sphere. Why is it that shape and not a sphere around our sun?
Yeah, I think it starts out as not the best cartoon to see, but it does start spherical-ish, let's say, and there's lots of attempts to sort of map, taking radio waves, looking through different directions, trying to map exactly what it looks like, and it is sort of spherical-ish initially, but because we are moving at, you know, we're moving around the Milky Way at, you know, a couple hundred kilometers a second. So we're moving through an interstellar medium. So once you get outside of our immediate surroundings of our solar system, you've got the background not perfectly smooth because we're inside of this bubble as well. But as this heliosphere is being pushed out, it's pushing into regions where the local bubble is a little less dense and regions which are a little more dense. And we're moving at a couple hundred kilometers a second as a whole as we're moving through it. So all of those things sort of sculpt and shape, and it changes in kind of real time. I looked it up about a year ago. People have sort of been mapping this thing almost regularly, and they can sort of map almost in real time, and it does change. Not maybe the inner part, but the outer part does sort of modify in terms of its shape as it's, you know, as we're trundling along at a couple hundred kilometers per second. And it's one of these things that not many things we can see change on relatively short timescales, but the outskirts of that heliosphere you can see changing shape on, I don't know, years or decades time. I don't know the exact number, but yeah.
Next question.
Brad, thank you very much. That was a really interesting talk. Could you give us some idea about the comparative densities between inside the heliosphere out into the intergalactic media, and then further and go out into the intergalactic media?
Yeah, I mean, it can go many orders of magnitude, certainly from when you're going from the background interstellar medium where you might have anywhere from, let's see, a few tenths of tens to hundreds of, you know, the high density regions, you might have tens to hundreds of atoms per cubic centimeter. You know, when we think of star forming clouds, where those clouds are, you can have hundreds, if not thousands, tens of thousands of atoms per cubic centimeter. If you average it over the entire galaxy, you're probably getting down to, a fraction of an atom per cubic centimeter. If you're going, and that's if you just took everything and spread it over the entire galaxy. So from high dense regions to kind of the average, again, you have many orders of magnitude, factors of 10,000, 100,000, ish, something like that. Inside of the bubbles, though, you can again go down, not factor, we're not talking factors of hundreds of thousands, but factors of hundreds, let's say. Don't know the exact numbers, but you are significantly lower. You're not at the level of the intergalactic medium where there's, other than there are various gas clouds here and there, but you're not at, you're not swept up, to leave behind a perfect vacuum, if you like. But you'd be several orders of magnitude. Probably, it's not a factor of 1,000, not a factor of 10,000, but probably, I don't remember the numbers now, but I would guess at least a factor of 10, factor of 100. So a couple orders of magnitude difference in the lowest density regions of these bubbles compared to the surrounding interstellar medium. And then many orders of magnitude below the high density gas clouds where the action of star formation sort of occurs in ballpark numbers.
Thank you.
Thanks, Brad. First of all, thank you for the disembodied Elon Musk. I don't think I'll sleep tonight. The bubbles that you were talking about, the local bubble and the, if you like, the solar bubble, how do they interact to form star-forming regions? Is it at a local bubble level or is it at a bigger level?
Yeah, it's a very good question. And in fact, this is still a hot topic of debate. Is basically you can form a star. The density has to get above, the sort of numbers I mentioned there. The density has to get above a certain threshold. So if you have a ton of gas but it's spread over a huge distance, it's not going to form anything. So you either have to bring this gas together so it gets dense enough for nuclear fusion to occur, so for a star to form. And you can do that in different ways. You could, if there's sufficient gas sort of floating around and there's a lot of it, even if it's spread over a big distance, gravity will slowly try to bring this stuff together. And so you might be able to, without even worrying about bubbles or any other nonsense, if the gravity is strong enough, it can pull the gas together, form a star. But if you can make things a little bit easier by having this gas which is floating around, but then you think of it almost as a shock wave, but as a bubble sort of sweeps through it, it just collects it and shovels it up. And so at the front end of that, the gas is piling up and it's getting denser and denser and denser, and eventually it can get dense enough that it could form stars. So even without gravity collapsing and getting dense enough to form stars, you've just basically taken something from the outside and rammed it into it to cram it together to make it dense enough to form stars. And so there's a lot of debate as to, right now, what is the relative role of, you can also do it potentially with, if you've got strong magnetic fields, strong magnetic field can take some of the charged particles inside this gas and help confine it and make it dense enough to form stars. So you could have, if you like, the pressure of a bubble, you could have just self-gravity pulling it together. You could have magnetic fields helping to confine it and make it denser. So all of these play the same role of just getting the density high enough to form stars. And so which one is the most important, though, kind of depends a little bit on, I've seen computer simulations that do everything with magnetic fields, and they look, wow, that looks just like a star forming region that I see in JWST. And then you get one that's done completely with shock waves pushing things around and getting all this filamentary structure on the surface of bubbles. Like, oh, that looks just like what I see in JWST. So I think we don't have the exact answer right now as to how much of it is turbulence, how much of it is shock waves, how much of it is self-gravity, how much of it is magnetic fields. There's a lot of debate on it. All of them work in the same direction of increasing the density to allow you to form stars. But it's clear that some of it is going to be driven by bubbles. You can, when you take these beautiful high resolution pictures that people now get with infrared facilities like JWST, and you can see, you know, filamentary structure of star forming around areas where there are bubbles. It's clear the bubbles have made it easier, have aided in perpetuating the star formation around these regions. Cyclic star. Yeah. But yeah, I saw there was a press release just in the last couple days. I can't remember where I saw it. It was just in the last few days where, again, someone's trying to use the magic of AI to throw in a ton of data at it to try and find a simple formula that says this much is gravity, this much is magnetic fields, this much is pressure, this much is shock waves. I saw the press release, but I didn't go to read the paper yet. My gut feeling is it's probably nonsense, but that's probably my AI bias coming into play right now. But anyways, it just reflects the fact that even from, you know, doing my PhD 30 years ago plus, people were still debating how much of it is, what actually causes star formation. Is it all self-gravity? Is it external influences blasting and pushing things around? And 30 years on, we've got beautiful, beautiful images, but I don't think we have the answer to exactly how much of it is coming from these things and exactly how important it is. But it's clear that bubbles and the sweeping up does help in forming stars. You can see them trace, some of the star formation traces the shape of those bubbles. So it clearly is playing a role, whether it's the dominant role, I don't know.
No questions online as of yet, so we've got another one in the room.
Fantastic lecture, thank you. Many years ago, I went to a lecture by Houghton R.
Yep.
That was entitled The Electric Universe. And he was talking about magnetic field lines and huge currents flowing in the universe, helping to shape the form of galaxies.
Yeah. Yep. I know that the electric universe has got a lot of bad press that's been applied in different ways to maybe applied incorrectly in some cases. In that particular case, though, yeah, magnetic fields absolutely do play a role in helping to shape a galaxy. Probably in things like elliptical galaxies where everything is turbulent and messed up, yeah, there probably is some magnetic fields, but they don't play a dominant role. But in galaxies like the Milky Way, yeah, I think we do have a magnetic field that spreads through our galaxy, just like we've got a magnetic field that spreads around our atmosphere, if you like. We have a magnetic field that helps, I think, preserve the lovely grand design spiral nature and helps to keep things thin. The way that magnetic field is confined does help, absolutely. So that is, again, something, you know, we've known about magnetic fields for a long time, but including them in computer simulations, you know, when I was doing my work 15, 20 years ago, people were just starting to, you know, people had done for individual star forming, some of these individual star forming regions, which were very idealized. They did include the magnetic fields, and you could see the magnetic field helping to shape the star forming region. And we knew that the galaxies had a magnetic field, but because the simulation size was just so big, we couldn't capture the physics of the important physics of the magnetic field, because that happens on a much smaller resolution scale, if you like, than the gigantic. It was clear that it was there. It was clear that it had a role, but basically it was ignored. So there's a whole cottage industry, magnetohydrodynamics, which is basically hydrodynamics, but including magnetic fields. And it has existed, like I said, for a while, doing star forming regions, but it's only really taken off in the last 15 years when people now are doing galaxy scale simulations where they include gravity, where they include these exploding stars and the bubbles. Some of them include cosmic rays, and some of them are now including magnetic fields. It's really computationally expensive to do. And so typically they have an idealized kind of perfect galaxy, which they thread with a magnetic field, and they look at how the stabilizing influence of the magnetic field. And it's clear it does play a role in helping keep disks nice and thin and helping them extend. So it only helps improve the agreement, because even the ones I showed you that we had generated, to the eye, they look really good, but they're not perfect. They are still a little bit too thick and probably not as extended as they should be. And I think if we'd had the capability 15 years ago to include magnetic fields, I think that would have squished our discs a little bit more and made them a little bit more extended, made them even look better to the eye. So yeah. So I think that part of it, if you think of the electric universe, that those magnetic fields associated with galaxies like the Milky Way will absolutely help them be just that little bit better.
Can I follow that up, please? So when you're talking about your models, you're doing your dark energy, all that kind of stuff, then you're doing your viscosity. It's like a law of diminishing returns, I take it, by adding the other terms, magnetism and whatever. So what do you think's missing?
I think if I was for galaxies like the sorts of galaxies that I was showing you there, I don't think we're missing anything, but whether we are we've made one appear more important than the other. So, if you looked at our work, which looked beautiful to the eye, and we had this balance between supernova and stellar winds, those numbers would change a little bit because we ignored magnetic fields and we ignored cosmic rays, and they, if we had included them, they sort of got swept under the rug in some sense, or included in the role of, the cosmic rays push things around, but they return to the interstellar medium on a similar time scale to the high mass stars that I talked about before. So we would just sort of hide that effect inside of our term. So now people are starting to include cosmic rays separate from the winds, and people are including magnetic fields as a separate term now. So I don't think there's anything missing, but it may change the balance between the relative importance of each of them. So I've said how incredible stellar winds are, but if we look, come back in sort of 5 or 10 years when the next generation of simulations include magnetic fields and cosmic rays, call it correctly if you like. Maybe it won't be equally important with supernova. Maybe instead of being 50-50, it'll be 50, 30, 20, 10 or something like that. So I don't think there's anything missing, but the relative importance of each of them, kind of the devil's in the details, with some fine tuning that will happen over the next 5 or 10 years. I can't think of anything else that's missing.
Thank you.
Thank you very much. So we do just have someone online, Peter Lloyd online. So Peter, if you want to unmute yourself, I see that you've got your camera on.
Yes, thank you, Lars. Thank you, Brad, for another very stimulating and interesting talk about an aspect of things that I personally knew nothing about whatsoever. Yes, it's a simple question, I hope. You said that dark matter doesn't have viscosity. How do you know that it doesn't have viscosity?
I think that is a fair point, Peter. I think the simplest, if applying Occam's razor, then the simplest models that have been postulated for dark matter are, as I described, only interact through gravity. But there are variants of dark matter. People will talk about self-interacting dark matter. There are different flavors of dark matter out there that, and in particular, I'm thinking of self-interacting dark matter, which people suggest has a cross section and it can collide and do things. But those are even more speculative, let's say, than the classical dark matter. So no, we can't put hand on heart and say absolutely no, they don't feel viscosity in that sense, or they don't interact with each other in a non-gravitational way. People have suggested it. It's just that the data as it stands today is slowly pushing away some of those corners of parameter space that allows for some of these more interesting variants of dark matter. And so I think it'll become a little bit clearer over the next 5 years when things like the Euclid mission, which is up there right now, finishes all of its work. Some of the ground-based experiments trying to attempt to detect dark matter. Those are the things that are sort of pushing away into the corners of allowable parameter space for what dark matter be. So you can't right now put hand on heart and say 100%, this cannot possibly be viscous or self-interacting. There are some clever people out there who suggest that it could self-interact. You really have to fiddle a bit with the computer simulations to get things that look like the real universe plus individual galaxies and the structure of those galaxies when you allow the dark matter to have some non-standard properties. You can't eliminate it, but it's a little trickier.
Well, yeah, thank you. I think you've actually answered my follow-up question, which was going to be that does that mean that dark matter doesn't interact with itself? And you're beginning to say that some people think it might.
Some people think, yep, you can Google self-interacting dark matter, SIDM. That is one of the families of dark matter that are out there that suggests, but it is tricky. And there are computer simulations that people have used this variant of dark matter. You can do it, but you do have to fiddle things a little bit more than you do with the classical one. Doesn't mean it's wrong, just it's a little trickier.
I think you're tending to strengthen my disbelief in dark matter. Thank you.
Thanks, Peter.
Okay, thank you very much.
Brad, could I just go back to bubbles for a moment? And is our star, has our star formed in the bubble? Is it moving through the bubble? What's its relationship with the bubble other than we're in it?
Yeah, it's a good question. Where were we 5 billion years ago? You would, yeah. I don't think we know the answer to that one in terms of. I think we've been in a bubble for a while, though. I would guess, or at least we've had our heliosphere in place for a while, right? Because we've had life,
stellar bubbles you were talking about.
Yeah. So for the bigger bubbles, like no, I mean I don't think we have the ability to. We can wind the clock back. With the Gaia mission, we've been able to track how stars are all moving relative to each other with incredible precision. And you can only really wind the clock backwards a few tens of millions of years, or forward a few tens of millions of years to see exactly how our local neighborhood, if you like, would look like 10 million years ago. The errors increase so much as you go back further and further that it's more or less impossible to tell, say, 5 billion years ago when our sun formed, exactly who was near us and who wasn't, because the orbits have nudged and jostled and changed a little bit such that we can't tell where we were exactly 5 billion years. We can do ballpark numbers and say takes us, we're going 250 kilometers a second and we're going around like this. So we can play the game and take a wild guess, but everything has moved so much on that sort of time scale.
So we've no idea what our motion is through the bubble.
We have an idea now, but that bubble probably formed over the last 10, 20, 30 million years. From 10 million years ago was the last time a star exploded near us. That was about 10 million years. Yeah, 10 million years ago. That was about 100 light years away from us when that one exploded. So a bit closer than sort of Betelgeuse or Antares. And so that would have helped shape the bubble as well, that energy injection. But that was only 10 million years ago. Where we were 5 billion years ago, who knows? We could have been in a, we were probably in or near a spiral arm, because most of the stars form in or near spiral arms. So we were probably in one, even though we're kind of between spiral arms now, but we drifted a little bit over the last 5 billion years or so. So yeah, there's no way we can, and we'll never be able to get the answer to that one. There's just too many things change on timescales of tens of millions of years that winding the clock back further becomes impossible. And stars have exploded and disappeared over that sort of time scale as well, and we can't find them anymore. So yeah.
Okay, thank you for that.
Roy?
Thanks, Brad, for that talk. Just curiosity on your models. Are you able to set parameters that make the difference between, say, barred spirals and ordinary spirals? And why are ellipticals just confused masses?
Yeah, because there are the other thing which comes into play, which kind of ignore, I talked about the role that supernova and stellar winds and magnetic fields and cosmic rays, they all contribute to shaping sort of the internal structure and what type of galaxy you may end up with. But the other thing that plays a huge role is the environment that you are in. If you are in a region like where you've got a lot of things that are running into each other, so clusters of galaxies in particular, that's where you find lots of ellipticals, because you take a few spiral galaxies and they start to run into each other, and they get all jostled up and they form ellipticals. Come back in, a few billion years from now, when, Andromeda is moving towards us, and sort of 4 or 5 billion years, they will merge. And so those two spirals will be gone. If you're around the time when the sun is dying, is also when the Milky Way dies, you'll have a new elliptical galaxy will result. So regions which have a high density of galaxies means that you have an increased interaction rate between the galaxies. And yes, sometimes if you've got two galaxies that are, you've got a little one spinning like this, and a little one comes in the same direction, it may not cause massive damage. We've been absorbing little galaxies, the Sagittarius dwarf. We're in the midst of kind of shredding the Magellanic Clouds, but we're still a spiral. But if those were a little bit more massive, or had an orbit that took them in a different way, that would really change the structure of the galaxies. So we think ellipticals largely form in regions where there's just a lot of stuff happening. In our local group with M31 and Andromeda and us, pretty sedate, not a whole lot going on. So when you form a spiral galaxy, those internal things that I talked about can maintain it. But once you throw Andromeda and the Milky Way together, all the magnetic fields and cosmic rays and stellar winds in the world is not going to allow you to form almost impossible to form a spiral at the end. If you take two giant galaxies and smash them together, it all gets jumbled up and you form an elliptical. So that is something I swept under the rug, is environment and the interaction rate. That's really the thing that delineates between whether you're a grand design spiral or an elliptical. You typically find ellipticals in high density regions, spirals are more fragile, so you find them in low density regions.
Excellent. Thank you very much for that. So, as our normal master service would say, I think we've worked you hard enough. I think we've had plenty of questions, unless you're willing to take one quick final question.
What is stellar wind made up of? You said charged particles.
Yeah, so harks back to right at the very beginning. Your wind depends on the type of star. So like the sun, yeah, charged particles, any sort of charged particle that can get pushed by the strong, hot magnetized corona is able to push charged particles out from the sun. But for the stellar winds on these other systems are different. So, the ring nebula, which is being pushed out, that's basically the outer atmosphere of the red giant. A lot of it's cold temperature. So in fact, you've got lots of molecules and dust particles. So the wind is atoms and not super high energy cosmic rays flying away, but you've got like carbon atoms, nitrogen atoms, carbon monoxide atoms. So it can just be it doesn't have to be charged. It can, because it's the radiation from the star, if you like, or ring nebula, say the white dwarf down in that hot little white dwarf that's left over generates, at least for a period of time, a lot of high energy photons in the ultraviolet, and it's those photons that push right against the atoms and push right against the molecule or the dust particles themselves, and so they can't accelerate them up to crazy high speeds, which is why the expansion of the ring nebula is kind of slow, but it's the actual photons themselves which are pushing against dust grains and pushing against carbon atoms, rather than any sort of charged particle that's being accelerated from the magnetic field. So no, it's purely just a photon pushing against a dust grain or pushing against an atom or a molecule.
Okay, thank you very much, Brad. Yes. So, as I was saying, I think we've worked you very much hard enough this evening, and we did sneak a cheeky last question in there. Thank you very much for coming and visiting us in person. Wonderful talk, even I understood it, so that's amazing. So I think that just leaves us to give you a Mexborough and Swinton astronomical thank you.